Insulating a copper pipe. In this problem, we consider a cylindrical copper pipe that has heat transferring from the internal radius to the external radius, and we have isothermal conditions on either side of the thickness of the pipe. We're going to examine two scenarios, one in which the copper is bare, and a second case when the copper is coated in fiberglass to insulate it thermally. And the question asks, what's the heat loss difference between those two scenarios? Notably, we're not going to be considering convective losses in this example because we won't be covering convection until Payman takes over. So what we need to solve this problem are, first off, the thermal conductivities of fiberglass and copper, which you can obtain from just looking them up online. In the first case, we have no insulation, and so we're just looking at a bare copper cylindrical shell. The dimensions are shown here. And to calculate the heat loss, we're going to use Fourier's integrated equation for cylinders, which is given as we derived previously. And we can almost use this equation as is, except for the fact that we're not given the length of the pipe. And so in general, when you don't know what a dimension is, divide by that dimension because that means you don't have to calculate that dimension. So the value we're going to be looking for is not heat flow, it's going to be heat flow divided by length. And once we accept that, we can quite easily calculate that the heat flow divided by length is 414,000. The unit should be watts per meter. In the second scenario, we consider fiberglass insulation wrapped around the copper tube, and the temperature of the ambient is constant and the temperature inside the copper pipe is constant. So because we're adding an additional layer of heat transfer resistance, we know that the heat flow rate per unit length is going to have to vary to compensate for that. And our job is to calculate how that changes. So now we have a multi-layer cylindrical geometry, and harkening back to the way we calculated resistances in a multi-layer slab, we're going to do the same thing, but using Fourier's integrated form for cylindrical heat transfer. So looking at this, we see that the highlighted chunk of constants basically multiply delta T and relate to the inverse of thermal resistance. So we can write the thermal resistance for a cylindrical shell as the natural log of R outer over R inner, quantity divided by 2 pi Lk. For this particular problem, we don't want that L dependence because we don't have a value for length. So we'll divide both sides by L, and our thermal resistance loses that L dependence. Okay, so that's how you calculate the thermal resistance. Now we've got two layers through which heat is conducting, the copper and the fiberglass. So we're going to need to include a heat transfer resistance term for both of them, and just plugging that straight into the equation. On the denominator, the left-hand part is for the copper resistance, and the right-hand part is for the fiberglass resistance. And if you calculate these independently, you'll see that the fiberglass resistance is much, much larger than the copper resistance. And that's why fiberglass is a good thermal insulator. But plugging through the numbers to calculate Q over L, we see that the value is now down to 48.9 watts per meter, as opposed to over 400,000 watts per meter without insulation. So we've reduced heat losses by about 99% just by putting a thin layer of insulation on the copper. And that is how you can use multi-layer geometries to control heat transfer. Thanks for watching.